Hello everybody, I'm back with another video on the energy unit. We are working on homeworks numbers 4 through 7 today, which is basically the rest of the homeworks, the last half of the homeworks. And let us begin. It says, calculate the potential energy, kinetic energy, mechanical energy, velocity, and/or height of the ball at the various locations below. Use G equals 10 meters per second squared for simplicity. Okay, the problem obviously does not include friction because in this problem, this is a perfect world where there is no friction or air resistance, and we don't have to worry about that. But continuing on to the problem, in location number 7, the mass is 50 kilos, the height is 4 meters, and our gravity is 10 meters per second. So it's just mgh because that's our potential energy. And because the ball is not in motion, it's just there, it's just standing there, like you're on the top of a water slide or something. The kinetic energy is 0 joules. And the potential energy, which is mgh, comes out to be 2000 joules. And some of the reasons why we use 10 meters per second squared is, again, for simplicity. Like, this is basically mental math. I mean, it's pretty easy to do. You don't even need to punch it into a calculator at this point, which is why some schools, even some countries, actually use 10 meters per second squared instead of the 9.8 that we're so accustomed to here. And in position number 8, our potential energy is 1500 joules. Again, you can actually calculate mg to be 500, and then all you need to do is find the height because the mass and the gravity don't change. And so 500 times 3 is 1500 joules. 2000 joules minus 1500 joules equals 500 joules because, again, the mechanical energy does not change throughout the course of this roller coaster ride, or whatever you want to call it. And so mechanical energy is just 2000 joules, 2000 joules, 2000 joules, and 2000 joules. And that's how you figure that out. And we know that kinetic energy equals 1/2 mv squared. But instead of having to rearrange it every time, I rearranged it once, so it's in terms of v, our velocity. And we find out that velocity equals 2 times our kinetic energy divided by the mass, all over that raised to the 1/2 power. And so our velocity is about 4.47 meters per second squared. And at position 9, the height is 0. So that means that our potential energy is 0 because of mgh. And that means that kinetic energy is 2000 joules because 2000 joules minus 0 joules is just 2000 joules. And again, we plug it into our already rearranged equation in terms of velocity, and we get about 8.94 meters per second. And finally, for our final position number 10, our kinetic energy is 900 joules. Again, we are using 1/2 mv squared. Not the rearranged one this time, just the regular one, because it's asking us to solve for the height. And for kinetic energy, it's 1/2 times 50, which is our mass, times velocity, which was given to us at 6 meters per second. Punch all of that into your calculator, you should get 900 joules for your kinetic energy. And from that, 2000 joules minus 900 joules equals 1100 joules. And 100 joules divided by 500 equals 2.2 meters. And that's it for problem number 4. Alright, on to homework number 5. Number 1 says, Jamie lifts her toys into a treehouse using a homemade elevator. The elevator has a mass of 2.5 kilos, and the treehouse is 8 meters above the ground. How much work does Jamie do when lifting 5 kilos of toys into the house? Determine the power used to lift the toys in 5 seconds. Alright, well given that we're not given, but we already know that potential energy is mgh, which our mass is 7.5 kilos because we added two masses up together. Our gravity obviously is 9.8, and our height is 8 meters because we're 8 meters above the ground. All we need to do is multiply them, and we get 588 joules. And it also asks for the power, but that's pretty easy. All we need to do is have the answer that's already given to us, that we just got, divide that by 5 seconds, and we get 117.6 watts. And power, obviously, the units is watts. And that's it for number 1. Number 2 says, Mike pulls a sled across level snow with a force of 225 newtons using a rope that is angled at 35 degrees. Determine the work done if he pulls the sled 65.3 meters. And how do you determine the work? If you remember from some of our previous units, it's simply force distance cosine theta. All you need to do is plug in our force, which is 225 newtons, times our distance of 65.3 meters, times cosine 35 degrees. And make sure that your calculator is in degree mode and not in radian mode, because you're going to get a completely different answer and you're going to make a huge mistake. Just make sure to double check that every time. And number 3 says, calculate the kinetic energy of a 750 kilogram compact car moving at 100 kilometers per hour. How much work must be done to slow the car down to 50 kilometers per hour? Well, the first thing we need to do is convert our 50 kilometers per hour to meters per second. And after we do a little bit of conversions, we get 13.8 meters per second. I put a dash over there because the 8 is repeating. And that is the amount of work needed to slow down the car to 50 kilometers an hour. It's 216,983.8889 joules, because it's just 1/2 mv squared times 3. So that's pretty much it to this problem. And the reason why it's times 3 is because if you think about it, 100 kilometers an hour, that's double that. So it's 4 times. And so 4 minus 1 is just 3. So that's why it's 3 times half times 750 times 13.8 squared. And that's it for number 3. And number 4 says, Julie has a massive 49 kilos. What is her potential energy when standing on a 6-meter diving board? Julie jumps off the diving board. What is her kinetic energy right before she hits the water? And how fast does Julie hit the water? And do you remember that in this case, that right when Julie's about to jump off the diving board, and at the moment right when she's about to have contact with the water, that the kinetic energy and the potential energy all the exact same. And so we have our mgh, we have our mass of 49 kilos, our gravity is 9.8 as usual, times our 6 meters, and we get 2,881.2 joules, which is both our kinetic energy and potential energy. And we just killed 2 birds with 1 stone, which is nice. And the last part asks, how fast does Julie hit the water? Very simple. All we need to do is plug in our kinetic energy, which we just got, equals 1/2 mv squared. Do a little bit of rearranging, and it's pretty easy to find out velocity to be about 10.84 meters per second. And number 5 says, an unfortunate skydiver's parachute fails to open. If the diver hits the ground going 300 meters per second, determine the height from which the ill-fated jump is made. Again, just like with the previous problem, the point where the jump was made and the point where he's about to hit the ground is the same, and so the potential energy and the kinetic energy are equal to each other. So 1/2 mv squared equals mgh, and we have 1/2 v squared equals gh. So 1/2 times 300 squared equals 9.8 h, and our height is approximately 4,591.84 meters. And you notice that the problem doesn't say the skydiver's mass? It's because you don't need the mass, because what I just showed you is the mass actually cancels out. Number 6. A pendulum is constructed from a 7.26 kilogram bowling ball hanging on a 2.5 meter long rope. The ball is pulled back until the rope makes a 45-degree angle with the vertical. Determine the potential energy of the bowling ball. If the bowling ball is released, calculate the bowling ball's kinetic energy when it reaches its lowest point, equilibrium. What is the speed of the bowling ball at its lowest point? Okay, we need to first calculate the height, because it's asking for the kinetic energy and the potential energy, and the reason why it's asking for it, I'm saying for this, is because we need the potential energy, and potential energy is mgh. And I'm not sure if you can see my picture, but this is 2.5 meters. That's 2.5 over square root of 2, and so the little height that's from here to here is 2.5 minus that, which is 2.5 minus 2.5 over square root of 2, which is our height, times our g, which is 9.8, times our mass, which is 7.26 kilos. And we find that our kinetic and potential energy is about 52.1 joules. And determine the potential energy of the bowling ball, which we solved. And we also solve for the kinetic energy when it reaches its lowest point. And finally, it's asking for the speed. Again, it's square root of 2 times our kinetic energy over mass equals v. If you plug into our rearranged equation, you should get about 3.79 meters per second. And that's our final answer. Final two answers. Number 7 says, a dock worker places a 350 Newton crate on the top of an incline which leads to the warehouse. The incline is 8 meters long and sits 5 meters above the warehouse door. If the force due to friction is 50 newtons, find the velocity of the crate at the bottom of the incline. Okay, at the start, it's simply our force, which is given, times our distance, which is 5 meters. So in essence, mg is just 350 newtons. And our potential energy is 1,750 joules. But obviously, we have to be careful here, because the potential energy will not equal the kinetic energy, because some of the energy will be converted thanks to friction. And the friction given to us is 50 newtons. So the work going against the crate is 8 meters times 50 newtons, which is 400 joules. We subtracted two numbers to get 1,350 joules, which is the amount of energy, which is the amount of kinetic energy. And again, all you need to do is plug in those numbers, since we know kinetic energy is 1/2 mv squared. And if you do a little bit of rearranging, your velocity should be about 8.69 meters per second. Number 8 says, the cable of a 4,000 kilogram elevator snaps when the elevator is at rest on the 3rd floor of an office building, 12 meters above ground level. A safety device clamps the guide rails of the elevator shaft, so a constant frictional force opposes the motion of the elevator. If the elevator hits the ground level with a velocity of 10 meters per second, find the frictional force exerted by the rails. Okay. This is kind of like number 7, except it's asking us for a different part of the problem. The velocity is given to us. the mass is given to us. So that means we can use 1/2 mv squared to find our kinetic energy. It's 1/2 times our mass, which is 4,000 kilos, times 10 meters per second, that's squared, and you get 200,000 joules. And our potential energy is 4,000 kilos, which is our mass, times our gravity, times our height, which is 12 meters, and you get 470,400 joules. This number minus that number equals 270,400 joules, which is the amount of energy that is so-called lost. It's really not lost. It's simply just converted into heat or other forms of energy. And I should put this in quotation marks. I forgot that. But basically, you are so-called losing some of that energy because it's going slower. So you think you're losing it, but again, I'm quoting it because you're not really losing it. And the energy that's converted into heat, the energy thanks to friction, is that number, 270,400 joules. And that means that, and since our distance is 12 meters, all you need to do is that number divided by 12 to get 22,533.3 repeated newtons. And the last problem for this homework, number 5, is a 70-kilogram diver steps off a 10 meters tower and drops straight down into the water. If she comes to rest at 5 meters beneath the surface of the water, determine the resistive force exerted on the diver by the water. This one's a little bit tricky because I actually made a mistake on this the first time because it's not 70 times 9.8 times 10. You don't just like stop there at 10 meters because the diver is still going 5 meters down the water. So in reality, it's 10 plus 5, which is 15 meters. So you multiply those together to get 10,290 joules. And that divided by 5 meters, which is, we're trying to find the force of the water, which is 2,058 newtons. So you have to be careful on that one. And even I made a mistake on that one, so it even gets the best of us. And this is kind of like homework number 4. In an ideal physics world with no friction, it's asking us to calculate the potential, kinetic, and mechanical energies, velocity, work, and power of the ball at the various locations below. Again, it is using us to use g equals 10 meters per second squared for simplicity. Okay, for our potential energy, it's 200 joules because it's our mass of 10 kilos times our g, which is 10 meters per second squared, times our height, which is 2 meters, which is 200 joules. And our kinetic energy is 1,000 joules because it's simply 1/2 times our mass times v squared, which you get to be 1,000 joules. And then our mechanical energy obviously is 1,200 joules because you add them all up together. And our work, which is force times distance, is simply 1,000 joules. And our power, because it's happening over the course of 10 seconds, is 100 watts because 1,000 joules divided by 10 seconds equals 100 watts. And for position number 11, again, our potential energy is 100 joules because mg is 100 if you already can calculate that. So it's just that times the height, about 10 meters, which is 1,000 joules, and that means our kinetic energy is 200 joules. And just like the previous problem, we rearrange it to find our v. Sorry, not the previous problem, homework number 4. Again, it's 6.32 meters per second. And while the numbers are obviously different in this homework, it's basically the same concept again. So it's pretty easy and straightforward. 100 times our height, which is 5, to get 500 joules. And from that, we can solve that to be 700 joules. plug that in into our rearranged formula, and we get 11.83 meters per second. And since the height is 0, it's simply 0 joules for potential energy. That means all of it is kinetic energy, which is 1200 joules. And plugging it into a rearranged formula again, we will get about 15.49 meters per second. And for the last position, position number 14, our height is 7 meters, so 7 times 100 is simply 700 joules. Subtract both of these numbers together and you get 500 joules for kinetic energy. And plugging it in again, we get our velocity to be 10 meters per second, exactly for once in this case. And that's it for homework number 6. And finally, homework number 7. Number 1 says, a 4-bladed ceiling fan rotates with an angular speed of 30 radians per second. The length of each blade is 0.6 meters, and the mass of each blade is 2 kilograms. Each blade can be approximated as a uniform thin rod that rotates about one end. Determine the total rotational kinetic energy of the fan. If you actually go back to a previous unit, you'll actually be given the moment of inertia for most of the shapes. And we find out that our moment of inertia, in this case, just so happens to be 1/3 ml squared. And so we first calculate our moment of inertia, which is 1/3 times our mass of 2 kilos times our length, which is 0.6 meters. You solve that in, so it's 1/2 times 0.24 times 30 radians per second, because that's our omega. And so we get 108, and we multiply that 4 to get 432 joules. And remember, it asks us to determine the total rotational kinetic energy, so don't forget to multiply by 4, because I made a mistake first time, and I got 108, but all I need to do is multiply by 4. So you gotta be careful, because again, sometimes the best of us makes mistakes. And number 2 says, a flywheel is a solid disc that rotates about an axis perpendicular to the disc through its center. Rotating flywheels provide a means for storing energy in the form of rotational kinetic energy, and are being considered as a possible alternative to batteries in electric cars. The gasoline burned in a 300-mile trip in a typical mid-sized car produces about 1.2 times 10 to the 9th joules of energy. How fast would a 13-kilogram flywheel with a radius of 0.3 meters have to rotate in order to store this energy? And we are given that, and if you remember from our green formula sheet, that if you want to find the rotational kinetic energy, it's 1/2 I, which is the moment of inertia, times omega squared. And just so happens that our moment of inertia in this problem is 1/2 mr squared. So I put that in. So it's 1.2 times 10 to the 9th equals 1/4 times, because 1/2 times 1/2 is 1/4, times our mass, which is 13 kilograms, times our radius, which is 0.3 meters, times our omega squared, which is what we're trying to solve. If you do a little bit of punching into the calculator and rearranging, you should get 64,051.26 radians per second. So this is actually kind of easy, because it's just mostly plugging in and rearranging. And this one actually is a little bit more difficult. And to be honest, I actually kind of struggled on this, but I eventually got it, and it's actually really easy once you get it. I got it for the most part because, again, we're finding we have this equation, which I'm sure you guys went over with in class and you remember. So we don't have any, this is from starting from rest, and this is the speed at the bottom of the hill. Starting from rest, there's no kinetic energy, you're not moving, So both kinetic energies are crossed out. And obviously, at the final speed, there's no potential energy. So that can be crossed out. So thankfully for the left side, it's simply mgh, but the right side is 1/2 mv squared plus 1/2 I omega squared, which I, again, is the moment of inertia. And since we know that and we just so happen to know that I equals 2/3 ml squared, so it's 1/2, you factor 1/2 out, and it's 2/3 ml squared. And you can realize that the problem at the beginning didn't ask us for the mass, because we don't need it. Because the masses, if you factor them out, they simply just cancel out. So it's just GH equals 1/2 times V squared plus 2/3 R squared W omega squared. And 2GH is simply 35.28 equals V squared plus 2/3 R squared. And if you do remember from one of our previous units, that omega times the radius is simply the velocity. So if you do a little rearrangement, omega is just velocity divided by radius. And if you notice, the radius cancels out. How great is that? So if you factor that out again, once again, it's V squared plus V squared 1 plus our 2/3, because the R squareds cancel out. So that's just 2/3 V squared. So we get 5/3 V squared equals 35.28. Multiply both sides by 0.6, and then raise that to the half power. You simply get about 4.6 meters per second as our velocity. And notice how the problem doesn't ask for our radius or our mass, because we don't need it, because if you solve it, both of them will cancel out. And that's it for this video. I hope you found this helpful, and peace out.